So this is pretty exciting because we are starting chapter 5 and we only have about 3 more sections left in the course, which is crazy. It's gone by super fast. But what I want to talk about today, 5.1, actually some of this, if you have taken college algebra from us or really any college algebra course, will have a lot of what we're going to talk about today. So I hope that some of it is a little bit of review, but why, you ask, is this all in a calculus course? So you've read through the section, I know you do. And again, the idea here is what we're looking at is exponential growth and decay. So one thing that is important to understand is that all of these models basically say that the population at time t of something, right? It could be of people, it could be of flies, it could be a bacteria, it could be the population of, what we're going to see is how much carbon is in something. That is considered a population. And again, the idea here is, what does this equation say then? This says that the rate of change of the population, right? That's what the left-hand side says because that's a derivative. So that's the rate of change of the population with respect to time, because that derivative is in terms of t, is proportional, sound it out, Sarah, to the actual population, at time t. Which kind of makes sense, right? So if my population is growing, it's gonna, based on how many people we have, that's how fast it's gonna grow because we have more people to reproduce. Same thing with bacteria. If I have more bacteria, then the rate of growth of my population will increase based on how many people actually are in the population. Same thing though with decay, all right? So if we're looking at decay, what happens is, if it's decay, what happens is this guy right here is negative, okay? Why would it be negative? Because that says that the rate of change, I'm decreasing, right? That would be my derivative is decreasing. So what we saw, if we let y equal p of t, and so we've seen this before. We saw this in, what section was that? I think 4.5 maybe? I don't know. One of the sections in chapter 4. Then what we see is that if we let y equal p of t, we see that this equation here just becomes y primed equals ky. And what do we know? We know that any solution to this equation right here, or one solution to this equation, has the form y equals c e to the kt. So remember you did that in your homework. How can I prove that to you really quick? Well, let's take the derivative of this. That would be c times k e to the kt, because the derivative of e to the kt, I just bring the k down. If we rewrite this a little bit, this says that I can just put the k in front. This is c e to the kt, okay? And then what we have then is that y primed equals k. Well, what was c e to the kt? That was my original y, equals y. So we've seen this already. And basically, that's really all the calculus we're going to do in this section, other than maybe talking about the rates of change. We're just going to actually, most of what we're going to do in this section is going to involve algebra, which could be scary because algebra sometimes can be the hardest part of calculus. So let's do a couple of, well, before we do examples, what I just want to write down is are some of these. So exponential growth. And if you read your book, you know that these are true, right? So exponential growth has this form, p of t equals c, but in this case that c for us will be the initial population, e to the kt, okay, where k is positive, and p sub 0, maybe not the initial, well, yeah, pretty much the initial population. Or it can really be any population, but you've seen that. Exponential decay. Now I could use exactly the same formula for decay. The difference is, instead of saying k is greater than 0, right here I would say that k is less than 0, but your book decides to bring in a whole new constant, and that's fine. And this constant right here, my friends, is called lambda. And so it's just a Greek letter. And this lambda is positive. So then if I take a negative of that, and this is decay, all right, exponential decay. And so we're going to look at a couple things here. I'm going to do 3 examples for you and then call it good. The decay we're going to look at is we're going to look at carbon dating, radioactive decay, and then we'll do a couple more. But for right now, I want to do one with exponential growth. And I just took this one from your book. So the examples I'm going to use today are just going to be from your book. They're either odd problems or they're evens that I didn't assign for you. And the reason I'm doing that is because I'm lazy. So I'm not lazy. I can make up my own problems. But if they're already there, let's just do this one. So pause the video right now if you want and go ahead and write these in your notes. And let's look at doing this. So population of Mexico City. So they give us some information here. So when we're solving problems like this is going to be a growth one. So I know I'm going to be using this formula, and it's important to understand what are the things we don't know. So we have to look at what is this constant right here. What we're really looking for a lot of times, not always, but most of the time, is what is P naught and what is K. So those are going to be the important things for us today. So let's look at this. So this says at the beginning of 1990, 20.2 million people lived in Mexico City, and the population was growing exponentially. This is pretty important, right? Why is it important that they tell us this? Because then we know we can use this exponential growth model. In 1995, right, the population was 23 million. Part of the growth is due to immigration. If this trend continues, how large will the population be in 2010? So if I want to know how large the population is in 2010, what I need to find is P of t. Okay, I need to find, remember what this function gives us. This gives us the population at time t. And I have a couple of points here. So I'm going to let t equals 0 correspond to 1990. Okay, and then I'm going to let t equal 5, then what would t equal 5 correspond to? That would correspond to 1995, right? Because I'm letting 0 be the beginning of 1990. That's going to be, so when I talk about initial population, I'm not talking about like the initial population of Mexico before people were even there. I'm talking about the beginning point of the data that we're given. So my initial population will be 20.2 million. Okay, so here's what I know. I know a couple of things. I know that if I evaluate my population at time 0, this is going to be 20.2. And let's remember it's in millions. And then also I know that P of 5, right, equals what? How much? 23 million. So I know a couple of things here. Now this is good. Well, it's all good because that means this number right here is P naught. That's our initial population, okay? And that is, and if you look up here, that kind of makes sense because if we let T be 0, you would get P naught e to the 0. But what is e to the 0? That's just 1. So that's why that constant in front is always going to be whatever I let T be 0. So here's what I know then. I know that P of T equals 20.2 times e to the kt. And I don't know kt yet. So what you're going to be doing in a lot of these problems, the work that's going to be involved, is sometimes finding this k. Sometimes they give it to you. Sometimes we need to find it. So what I'm going to use, the information I'm going to use to find that k, is this fact that when t is 5, P of t is 23, right? Again, I know I care about, right, what my population is going to be in 2010, but before I can even get there, I have to find this k. So I know that P of 5, right, that's the same as saying 20.2 e to the 5t. And when, oh, Sarah, yeah, I got it. All right, so e to the k times 5. 5 is time, so make sure that 5 goes into t. What was my population? It was 23. And now I just need to solve for k. So you hear me getting out my handy dandy calculator. Now, of course, sometimes this is the hardest part, right? And I understand that. So what am I going to do to solve for k? Well, first I'm going to get rid of that 20.2. So I'm going to divide both sides by 20.2, clicking away on my calculator. And so I get e to the k times 5 equals, I'm actually just going to leave this as 23 over 20.2 because it's a nice long irrational number, and so I want to be as precise as I can. So I'm just going to leave it like this for right now, and then we'll finish this up. We'll worry about it in a moment. So how do I solve for k? How do I solve for k? I need to get rid of the e. So remember, we take the natural log of both sides because natural log. Sorry, this is getting kind of squished, but we can handle it. So I'm going to take the natural log of both sides. Why do I do that? Natural log is the inverse of e. So what happens when I compose them is they undo each other. Boom. Done. I know. It's sad when I try and talk like cool kids. Cool people. All right, so let's simplify this a little bit. So what do I have? I have 5k. I really apologize for this being so messy. So I have 5k equals the natural log of 23 over 20.2. And then what's my final answer going to be then? This will give me the most precise value for k. So what you need to do is you need to do natural log, put parentheses in your calculator, 23 divided by 20.2. Make sure you close that parenthesis and then divide it by 5. So I'm going to go ahead and do that. You should be doing this too. And you should be making sure that you get what I get. 20.2. Close my parenthesis, divide by 5. All right, so let me tell you right now, k is usually not going to be a really big number. K should be like usually less than 1, sometimes greater than 1, but not too much more. And so I get k to be 0.25962. Now I usually go to about 5 significant figures. This is about 6 decimal places. Remember that 0 is not a significant figure. You probably don't have to go out quite that far, but I always just go out a little bit longer just in case. Okay, so what does this do for us? So hold on, let me get rid of some of this stuff up here so we can finish. Oh my goodness. Sorry about this. Oh, whoops. I didn't know that would happen. Oh well. All right, so what do we see that k, I hope you're following this. I'm just going to pretend you are since all you people out there can't actually talk to you. What I see is that my k is 0.02596. And what am I going back to? I am going, let's keep our eye on the prize here. I need to find I need to figure out this equation right here. So the good news is I now have an equation. The thing I was missing was the k. So look at what this function gives me now. This is 0.025962 times t. What does this function give you? It gives you the population of Mexico City t years after 1990. So what do I care about? I care about 2010. So 2010, last time I checked, is 20 years after 1990. So what am I going to do? I'm going to plug in the 20. Make sure that all this stuff is in the numerator, right? The k and the t, make sure it's in the numerator. And then I'm going to have it. And I'm going to thank the math gods every day that I was born in a time of calculators. 962 times 20. Make sure that 20 is inside the parentheses. And what I got was 33.95. Now we could go out a little further if we wanted to, but it says how large will the population be? So in 2010, the population is estimated to be, but we'll just say will be. Remember, this is a mathematical model, so it's not always perfect. And I know you're like, but Sarah, you told me math was everything that's perfect and true. Well, it is, but the problem is the world is not perfect and true. So it doesn't always follow the perfect and true math. All right, and that's how you do that problem. I hope that makes sense. That's all over the place now that I'm looking at that, but it just looks like fun. So again, what's the process here? If they give you 2 data points, if they don't tell you what k is, you need to use those data points. The first one you'll use as your p sub 0, and then the second one you're going to use to find your k. All right, so let's look at clear this out really quick. Let's look at another one. So what I want to look, so that was population, that was exponential growth. What I would like to look at now is exponential decay. So if you read that, I thought they did a pretty nice job in your book of talking about carbon dating. And so carbon dating allows us to determine how old things are. So this one actually isn't going to be too bad because they actually give us quite a bit of stuff here. So remember my formula, right, for exponential decay, P naught e to the negative lambda t, where lambda is my decay constant. And I think, and you should, not I think, you should read through example 5 on page 259 and 260. Gives a good explanation of why the decay constant, for carbon-14 is 0.00012. And it's because the half-life of carbon-14 is 5,000, what was it? 5,730 years. And again, what does that mean? That means after, so once an animal dies, after 5,730 years, half of the carbon-14 that was initially part of the animal will be remaining. So it allows us to date some of these old fossils and stuff. It's pretty cool. And wall paintings, apparently. Anything that holds carbon, so it doesn't have to be an animal. All right, so this says, in 1947, a cave with a beautiful prehistoric wall paintings were discovered in this town in France. I don't know how to speak French. Lascaux, I think? Lascaux? I don't know. Some charcoal found in the cave, so that's why this charcoal is what has the carbon in it, contained 20% of the carbon-14 expected in living trees. Okay, so this is basically saying that, you know, if we took the amount of carbon-14 in a living tree, this charcoal, so they're just comparing two things that are carbon. This charcoal, right, found in the cave contained 20% of that. And what the question is how old are the cave paintings? All right. So again, I want you to think about the population in this time. T is going to equal time. And then the population that we're looking at, P of T is the amount of carbon. This might be my last example because this video is getting a bit long. All right, so what do we know? We know that 20%. So first of all, what I know, these actually aren't too bad. I think you're going to see this isn't too bad. So I'm going to have e to the negative 0.00012 t, where again, P is the amount of carbon. So P naught is the initial amount of carbon that should have been in the charcoal, right, at that time. So if we know that the amount of charcoal at that time should have had the same amount as the trees, the initial amount of carbon, well, what is left? Only 20% of that initial amount is left in the charcoal. Remember, of in mathematics usually implies multiplication. So if I want 20% of the original, I would take 20%, which is 0.2, times the original amount of carbon, okay? And look at what we're asking for here. We're asking at what time does the amount of carbon, right, equal 20% of the original, okay? So let's look at what happens here and how we can solve this. I'm going to go ahead and the easy thing here, this will happen every time when you're using ones like this, is I'm going to divide both sides by P naught. So they're just going to cancel, and I get 0.20 equals e to the negative 0.00012 t. Okay, now how would I solve this again? I'm going to take the natural log of both sides. So you're going to get really good at taking these natural logs. When I take the natural log of the right-hand side, it cancels with the e. That's the whole reason I did it. And now I'm just going to divide by a negative 0.00, blah, blah, blah. So I have the natural log of 0.2. I should turn my calculator on. Natural log of 0.2, close your parenthesis, divided by a negative 0.00012. And what do we get here? I get that t equals 13,411.98. All right, so let's think about what this says. So this is pretty cool. I mean, this says that when they found this in 1947, right, they found that the estimated age of these paintings, which this stuff always amazes me, I'm just going to round up because it's years, was 13,412 years old. That's amazing to me. Cave paintings. That's so cool. Wall paintings in a cave. That's so cool. So that was in 1947. I mean, technically, if we take 2016 minus 1947, that's 69 years. So how old would it be now? Well, we can't ignore, right, that we have 69 years since it was found. So add that to 69. I could do that in my head, but I don't want to. So what is the estimated age of these wall paintings now that it's 2016? They are about 13,481 years old. Wow, so cool. All right, so I think that should be able to get you going. I gave you, that first example is an example of having to find your constant. So you could use that for the decay or the growth. So finding that K. And then the second example is an example of where you're actually given the decay constant, which is a little bit easier. And then maybe you're going to solve for T. So as always, let me know if you have any questions, if you want more examples, anything like that. Look at the fun sheet, look at the fun sheet solutions, and I'll see you next time.